Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use the solved equation of motion, meaning the function you get out of the equation of motion for a vibrating system, how to use it to describe the motion of the system you're looking at. So getting back to this mass spring example, I've got two previous videos here on analyzing the system. Video 1 was about how to write the equation of motion for the system using either energy methods or Newton's second law. Video 2 is about how to solve those equations. And video 3 is going to be what do you do with that solution. So just picking up on the same example I've been going through here, we're going to imagine that this object here with spring constant K of 500 Newton per meter. This 2 kilogram object, we're going to assume, is displaced from equilibrium 20 centimeters and released. Now, in the previous video, I talked about the solution of the differential equation, which looked like x equals minus a cosine root k over m times t. Now, this equation is only good for this example or other ones that are basically just like it. It's not good for all oscillating systems. Again, you have to go through the process of writing the equations and solving them. The point of this is now, what do we do with this guy? So I went ahead and put in the numerical values here. So A is 20 centimeters. Root k over m is approximately 16. I think I got about 15.8. I'm just going to round it to 16 for this video. Remember that we assume zero friction and no air drag and such anyway. So 2 sig figs is, I think, plenty good for just an instructional video. Then the question is, what do we do with this guy? Well, one of the things we want to be able to get out of this is the frequency of the system. That's always a very important thing for an oscillating system. So after watching this video, hopefully you'll know how to do that. And then second, what do we do with this guy? All right, so what I like to do with that equation that describes the system is graph it. If you have me in physics, you know I love my graphs. So the position function here, x against time, is a cosine wave. So I'm going to start with just a quick sketch of a cosine wave. If I were to graph just x equals cosine t, that has a shape that looks something like this. The cosine function starts here at the point 0, 1. This point right here, this distance on the graph, and this is an important fundamental for this. This distance right here on this graph would be pi over 2. From here to here, one complete cycle would be 2 pi. Those are important things to understand for kind of interpreting our results here. Now, we're not looking at a cosine wave. We're looking at minus 20 centimeters cosine omega t. Now, before I graph it, let me chat about the unit. I'm just talking about the motion of the system. Whatever I put in here, like centimeters, unit-wise, x will come out in centimeters. If I put 0.2 meters here, then x will come out in meters, and that's perfectly fine. As long as you're only studying the motion, this is a perfectly acceptable unit. The velocity will come out in centimeter per second, and the acceleration in centimeter per second per second. If, however, you wanted to use this equation to down the road express maybe something like momentum or kinetic energy or apply Newton's second law, you would want to use standard units of physics. But for just a motion study here, I'm just going to leave this in centimeters. So again, this isn't a cosine wave, it's a flipped cosine wave. So a graph of this function, might look something like this. Now there's one complete cycle. I'll go ahead and draw a couple of cycles. This point right here is an important one on the graph here because that point represents the system having gone through one complete oscillation cycle. And I'll get back to that here in a minute. Now, this represents the maximum value that this function is going to hit here, 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 and so forth. Same thing here, just in the other direction. So on this graph, that value here, x is equal to 20 centimeters. Here, x is equal to minus 20 centimeters. And what's going to happen is this thing is going to oscillate back and forth between x equals plus 20 and x equals minus 20. So we pretty well got the motion of this described. The other thing we want to be able to do is we want to be able to calculate times anywhere we want. Now I'm going to go ahead and pick a special time here. Right? This one. This one's special because, or at least partially special, it represents the time here, the location, where the system has oscillated through one complete cycle. Now, a very important thing to realize on the graph is that this is our time t. And at that point, this thing has to equal 2 pi. So at that point on the graph, we can write out the following equation here, that 16t is equal to 2 pi when we are right here on that graph. So that value of t here can be found just by dividing by 16. And what I get out of that is, looks like pi over 8. Now, I like to use actual decimals for these. Pi over 8 is around 0.39 seconds, give or take. So what that means now is that the period of the system is right around 0.4 seconds. It's going to take about 0.4 seconds for the system to start here, accelerate this way, come back to this location. The period and the frequency are inverses of one another. Right? That's just because of how they are defined. Period is the time to complete one cycle, so that thing's going to have units of seconds per cycle, and that's what we just found. Frequency is the number of cycles per second. So they are inverses of one another, so the frequency of this system is going to be 1 over the period, and that's going to be 1 over 0.39. And we get about 2.56, I guess I'll round that to approximately 2.6, 1 over seconds, or 2.6 hertz. So this is not a fast vibrational system. You know, lots of vibrational systems have frequencies a lot higher, and this is just a result of the numbers I chose. You know, relatively high mass, especially compared to the spring. I mean, 500 Newton per meter means you've got to stretch that spring an entire meter just to get a 500 Newton force. And remember that a 500 Newton force is still only a 100-pound force. So, and the system's only oscillating back and forth 20 centimeters. So the point of this video was how to describe the motion of the system once you solve the equations. And you do that graphically. Just take your equation, put in the numerical values, and graph it. Now to do that, you have to have some knowledge of sines and cosines. This is a relatively simple one. It's got only a cosine term. Sometimes these will be sine waves, and they can actually have both depending on the initial conditions. You could have both a cosine and a sine. In this particular example, the motion is described by a cosine wave, so I drew a cosine wave. A very important point on that graph is always one complete cycle. So here we are after one complete cycle. At that point, here's a very crucial thing to realize. This is equal to 2 pi at one complete cycle. That's what allows you to calculate the time on the graph that gets you the one complete cycle. That's called the period. And then the frequency is 1 over the period, in this case 2.6 hertz. Now, other things we can do with this function, we can calculate velocity against time. That would be the time derivative. I'm not going to do this in the video. It would be easy enough to do, though. We would just time differentiate this. We could also calculate the acceleration just by time differentiating our velocity function. And again, I'll save those for other videos here. So main point here is how to represent the motion graphically and how to get the period. And of course, from the period, how to get the frequency. So hopefully this has successfully demonstrated that for you. Have a great day.